Slavica Jonic, and she is research director at the French National Center for Scientific Research, CNRS, and she is a head of image analysis methods, developing algorithms for studying structure and dynamics of macromolecular complexes in the subgroup of bioinformatics and biophysics. She has worked a lot in the development of image analysis methods and computational tools for structural and dynamics of biological macromolecular complexes. And in particular, today, she will talk about HEMNMA and HEMNMA-3D, that they are two tools for in vitro and in situ studies of continuous conformational variability of macromolecular complexes.
Okay, so I think he already introduced my talk, so I don't have to re-explain what I'm going to talk about. So you will hear about these two methods, HEMNMA and HEMNMA-3D. The first is for single particle analysis, and the second for subtomogram analysis in terms of continuous conformational variability, and both are available in our continuous flex plugin within Scipion 3 currently. So here is the contents of the talk. I will first describe briefly HEMNMA that was introduced in 2014. Actually, it's a work in collaboration that we had in collaboration with the group at CNB in Madrid, particularly with Carlos Oscar Sorsano. So it is for analyzing continuous conformational variability in vitro. So I will briefly introduce the problem. And it is based on normal mode analysis. So you will hear about the method of normal mode analysis. Then I will present one, describe the method very briefly and show one example of its use, and then the protocol, how it looks like in Scipion today. And then we recently extended this to 3D analysis of subtomograms with missing wedge, of course. So again, it is about continuous conformational variability. So we'll hear about this new method. I will show you one example of its use. So this is part of a manuscript that we just recently got accepted for publication. So you will read about it soon. And then I will show you the protocol in continuous flex. So you will see the slides, and then I will conclude this talk. This is the first part of the talk, and then I will show you a live demo of the two protocols in Scipion. So biological macromolecular complexes change their shapes in order to accomplish various biological functions like protein synthesis, virus maturation, DNA replication, and these changes are not discrete, so that you don't have a few discrete states, but many intermediate states exist, and they are not countable. So we speak about continuous conformational transitions or gradual changes. So examples of these changes are, for example, ratcheting motion of ribosome 70S complex, in which one subunit is rotating with respect to the other subunit, or here you have an example of swelling of virus, icosahedral virus capsids. And then you have various different, more complex transitions, like opening and closing of complex flexion, like in this case, between the two lobes of this complex. And then you can also think about more complex changes, like a combination of discrete and continuous changes, like along the elongation cycle of ATS ribosome, in which many different ligands will bind and unbind, and this is also followed, combined with continuous changes. So what is the heterogeneity problem in single particle cryo-EM? In an ideal case, on the grid, you have a heterogeneity of orientations of macromolecular complexes, but identical conformations. In practice, however, you have a combination of the heterogeneity of orientations and conformations. And again, as I said, because the conformations are not few discrete conformations, but you have plenty of them, so it becomes extremely complicated to disentangle different orientations, different conformations of the complex, which is due to noise, particularly. For example, here you have some examples of synthetic projections without noise and with noise, and it is clear that even without noise, it is difficult to say whether some two images come from two different orientations of the same conformation or from two different conformations that may have even the same orientation. And with noise, this is even more complicated. So we developed the methodology that we called HEMNMA. It stands from hybrid electron microscopy, normal mode analysis. It performs conformational variability analysis in 3D space by using an elastically deformable 3D reference to simultaneously determine all parameters for each image, a single particle image, which means conformational parameters, orientational and translational parameters. This is performed by an iterative refinement of all these parameters through combined 3D to 2D elastic and rigid body alignment. So at the end, you get a representation of all images in a common space that we call conformational space or landscape. And inside of this space, you can analyze the distribution of points, which means each point is an image, and then perform some 3D reconstructions and obtain some molecular movies, animations of your motion of the complex. So in the methodology, we don't use classification during or after alignment. We instead use an interactive grouping of images with similar conformations after the alignment. The method is based on normal mode analysis, which is a simulation of the dynamics using a linear combination of independent harmonic oscillator types of movements. They have different frequencies. The lowest frequencies are collective motions that are like, for example, those that are related to the change of the shape, and very high frequencies are very localized motions, like those that are related to change of the bond angles and lengths. Here you see an atomic displacement with one normal mode of this blue structure into the red structure. So the flash, the arrows are the shifts of each of the atoms in the blue structure. Normal mode analysis can be performed using full atomic structure or coarse grain structure, or using a density map like those obtained by cryo-EM, or even simulated density maps from atomic structures. For this, if you have a density map, you need to convert it into a collection of points that will be then moved with the normal modes. So we get them using a conversion of the density into a collection of 3D Gaussian functions that we call pseudoatoms, and the centers of these Gaussian functions are our points that are then displaced with normal modes. So here these spheres are actually representing the 3D Gaussian functions. To calculate the normal modes, we use Tirion's elastic network model, in which atoms or pseudoatoms are connected with elastic springs, but only those atoms or pseudoatoms that are close to each other. And how close they can be in order to be connected is defined by a parameter that we call radius of interaction between the pseudoatoms or atoms, or cutoff interaction cutoff radius. So the potential energy function of the system is a sum of these potentials of that is based on pairwise distances between atoms, but only those atoms that are in the vicinity, and this is determined by this radius of the region R. So this is the distance between two atoms in A and B in the initial structure, and this is the same distance between the same two atoms in the displaced structure. So you have a squared difference between the two distances, and this is this term here that you see. In this Tirion stochastic model, network model, we assume that the given conformation, which means the reference structure, is our energy minimum conformation. So there is no minimization of the energy, and the normal modes are computed through harmonic approximation of this potential around this reference structure that is at the minimum energy. To get this harmonic approximation of the potential, we need to change the current system. Before the potential energy is approximated through Taylor expansion around the reference structure, where we keep only the second order terms. And then there is a current change from R to Q's. So we get rid of all these cross terms here, and we get only quadratic terms at this side. And this current change is actually equivalent to the diagonalization of the Hessian matrix, that is the second derivative of this potential energy function. This diagonalization is actually done through a solution of an eigenvalue problem, and the normal modes are obtained as the eigenvectors of the Hessian matrix. They are the columns of this matrix A, and the square frequencies are the eigenvalues of the matrix H. They are the diagonal elements of this matrix L. So the size of the Hessian full size is 3n times 3n, where n is the number of atoms, and 3 stands for the number of currents in Cartesian system, x, y, and z. So once you compute the normal modes, you can displace the currents of the initial model. They are given here as x, I, 0. Using a linear combination of these modes A, and the coefficients of the linear combination are Q's. We call them normal mode amplitudes. So these Q's are not computed through the normal mode analysis. In order to the way we are computing them is by correlating the models, displaced models, with the EM data. So, for example, single particle analysis, we are correlating these models with images, and in subtomogram analysis, we are correlating these models with subtomograms. So I should say that we are not using the first 6 modes. As you see here, you can have up to 3n normal modes. But we are starting actually from mode number 7. The first 6 modes are related to rigid body moments, and we are dealing with these moments specifically in our alignment method. We are combining rigid body alignment with elastic alignment, and this is how we deal with rigid body motions. Also, it is important to notice that these Q's, normal mode amplitudes, do not have physical units, and the physical units are at the level of currents and these normal mode vectors. So here is an example of how it works with images. You have a set of images and an input density map. First, this input density map is converted into, as I said, a 3D Gaussian function that we call pseudoatoms. Here, and then the normal modes are computed. Here, for example, you see one normal mode. These red arrows are displacement atoms with this normal mode for this pseudoatomic structure. So we have computed all normal modes, but we are not using all normal modes for image analysis, because this would, if we used all modes, this would be too time consuming. So we need to select a subset of normal modes, not any normal, but non-rigid body modes, which means starting from mode 7. So we usually use subset of lowest frequency and most collective modes. So we have a measure of the collectivity that is measuring how many atoms are moving together with the same mode. So it's a measure that is normalized between 0 and 1. So typically, if you set a threshold like 0.5, you will find what are the modes that are more collective than the others. So you can select those modes. So for example, here we selected 6 modes that had the collectivity above 0.5. Once you selected the modes, you then use them to deform elastically the reference and then compare with your images. So for each single particle image, we perform interactive 3D to 2D elastic and rigid body alignment, which means this deformable model is projected and projections are compared with the image. So we almost simultaneously find conformational parameters, orientational and translational parameters. The conformational parameters in our case, in our model, are the skews. So the normal mode amplitudes are determining our conformation for each image. So each image is analyzed independently from other images and in parallel with other images. So at the end, the Qs, the normal mode amplitudes, are projected onto a lower dimensional space, because sometimes you use more than 3 modes and you want to see all these images together in some lower reduced dimensional space. So for example, here we use 6 modes and we lower the dimension to 3. So we see all these images together, and close points are images with similar conformations, and those that are very far away are those images with very different conformations. So in this space, you can further either displace this deformable reference along the direction that you identify, and then you can compute with our graphical interface the animations, the molecular movies, or because for each image, each point here, we have through our image analysis, we determine 3 Euler angles, 2 in-plane shifts, plus the conformation. You can compute you can group the images and compute 3D reconstruction from the regions where you have that are more dense and where you have images that are close to each other. So here is how the graphical interface for this HEMNMA method works looks like in the latest version of Scipion 3. So you need to follow the protocol, like the steps 1, 2, 3, 4, 5, and then you will perform the whole protocol. I need to point out here that there is one part that is done like kind of to be pedagogical. We decided to make this available to people who just want to maybe compute normal modes and maybe don't want to analyze images. So they can do the first 2 steps and maybe stop here, or those who want to continue and compute analyze images using these computed normal modes, they can proceed 2 further steps and then do analysis of images and visualize all these results. So in the beginning, you need first to import either an atomic structure, as I said, or a density map. So in this slide, you see only how the tree is when we imported an atomic structure and analyze the images using atomic structure. But you will see in the demo that I will show you how you can also do this with density map. Because if you have a density map, then you need to also perform this step, that is conversion from the density into an atomic structure. And then you can compute normal modes by performing this step. So this is the step here. Then you import particles if you want to continue. So those are the images that are imported here. But if you want to play a little bit to see how this works with some synthetic data, you can now use this option here. We provided in this latest version the protocol to synthesize images with noise or without noise, with CTF, with random orientations of particles inside of these images, random shift, and so you can use this. Then you can also resize particles, resize images, which means make them smaller. This can be useful if your images are big and then you want to perform this analysis faster, and also can reduce the noise in your images, and you can get even better results by reducing the size. Then once you prepare the images, you perform image analysis with the selected normal modes that you first, of course, had to analyze at this point. So you will see how this analysis is should be performed. And at the end, you can reduce the dimension of the space, make some grouping of images, reconstructions, and animations. So this is the graphical interface that you will see when you and you should actually open if you import a density map as a reference structure. So this is the graphical interface to help you convert this map, gray, into a set of pseudoatoms here, these spheres. So each of our boxes has some default values of parameters that you can keep or you can change. I mean, if you want to play with some other parameters, you can change them. Typically, all these fields that have that are in gray are for more advanced users, and they maybe are less frequently changed. You have helps here, and you can open each of them to understand which is which parameter. So once you perform the conversion of the pseudoatomic structure, or you didn't perform conversion, but you have imported an atomic structure, you then can compute normal modes. So this is the graphical interface for the normal mode analysis. So this is the step 2, you remember, in the tree. So in this step, we have to actually decide whether we want to enter our interaction cutoff radius, which means the value of it in the field, or we want this radius to be computed automatically. So we recommend that for atomic structure you can use an externally entered value, and we have one by default. It is 8 angstrom for atomic structure, but for pseudoatomic structures we recommend to use this automatic computation of the interaction radius. And to say that you want it automatic, you need to select the cutoff mode relative here. Otherwise, which means what is recommended for atomic structure, you will have an absolute mode. If you select relative, then you will see this field with 95. This is the default parameter. This means that the interaction cutoff radius will be computed so that 95% of these pairwise atomic or pseudoatomic distances will be below this computed interaction cutoff. Then you have this threshold on collectivity. This is more like for informative purposes. So in a list of normal modes that you will obtain, you will see how we display the normal modes in textual form. You will see the collectivity computed for each of the modes, and those modes that have the collectivity below this value will not be checked, so the column enable will not be filled in. This is for the user to notice that these modes probably should not be taken into account for image analysis because they are very low collectivity modes. And then it is very important to understand that we are using actually two different approaches for normal mode analysis for atoms and for pseudoatoms. For pseudoatoms, we are using what we call Cartesian method, where the Hessian matrix is diagonalized, as I explained before in the slide before. For atoms, we are using another approach that is actually more suitable for big structures with a lot of atoms, a lot of points, like full atomic structures. So this method is called rotation translation block method, RTB, and it is actually decomposing the atomic structure into a set of blocks, rigid blocks, that are then moved all in translations and rotations. And the number of residues per block, in order to set the number of blocks, you can give here. So the default value is 10, but you can change this if you want. So this RTB method will actually make the Hessian much smaller. So it will be approximation of the Hessian, but a good approximation, in order to actually make this normal mode analysis faster. Again, this makes sense, especially with atomic structure. So we are kind of separated two. So for atoms you have RTB block method, and for pseudoatoms you have standard Cartesian Hessian diagonalization. So once you compute the normal modes, you can then animate them, like by setting this number here for each mode, like mode 7, 8, 9, you will analyze them using VMD. You will visualize the movies. But then also you can get some other information about the computing normals, like maximum atomic shift for all atoms over all modes. This is to see whether you have in your structure 1 or 2 atoms that are moving too much and they are isolated from other atoms. In which case, if this is the case, then you need to change the interaction cutoff radius, or do something else with the structure, like to put mass, to if the density map is your reference. These also isolated movements of some atoms you can also experience in these VMD animations. But these plots can be useful because quickly you can see that something may be wrong. And then you can display the list of normal modes with their collectivities, and you can then order the modes by clicking on this label. They will be ordered in descending or ascending order according to the collectivity, because by default they are ordered in the order of increasing frequency. So once you decided which modes you want to use, you are switching to the step next step. This is the image analysis. So you need to enter the number of modes you want to work with. Like here we wanted to work with mode 7, 8, 9. So you have 3 modes. If you don't fill this field, for example, all modes will be used. but it is recommended that you reduce the number of modes. We have one field here that normally should stay empty, but for us it is useful because we can quickly analyze the rest of the protocol, the rest of the tree. It can be useful for development and for tests of the protocols, because here we can insert the file that contains pre-computed results in order to be read and to go to the next field, step. But for the majority of cases, because you are going to run this, this field will be empty. So this is the tab input, and then you have the second tab that is that contains some parameters that are related to elastic and rigid body alignment. Here, what is the most important is to notice that there are two methods for rigid body alignment. One is real space projection matching, and the second is the one that is here written, and it is a default method that is variable projection matching in valid space, followed by another method that is performing refinement of rigid body parameters in Fourier space. This is based on spline interpolation. So if you use projection matching, your image analysis will be fast, but maybe less accurate, especially with noisy images. And if you use variance and splines methods, it will be slower, but more accurate. Here we have one parameter that is determining the discretization step for the reference library of projections. So first we compute library of projections with the step of 10 degrees, and we perform variable projection matching, and then we refine these parameters using this second method here. So once, and I would just comment on this field. Because we use trust region Powell method for elastic alignment parameters optimization, there are some parameters that are hard-coded in the code that control the convergence of that optimization method. And here we provide just one scaling method to scale the initial value of this initial trust region radius. So this parameter in principle should not be changed, but the user can change it if he perhaps suspects that the conformational change is not that big as he would expect or she would expect. So he can or she can change this from 1 to 1.2, 1.5, up to 2 maximum. So this should not be increased too much, but you can decrease it if you wish. So once you obtain this image analysis, and you obtained also you could visualize the results. So here you see all these points are the images in the space determined by the amplitudes of 3 normal modes 7, 8, and 9 that were used here. Then next step is that you can lower the dimension of the representation. In this case, where we go from 3 to 2 dimension, you don't see much difference, but when you started with more modes, then you will see the effect of this coarse conformational space. So in this space you see again, so those are the same images but in another space. In that space we can analyze the distribution of images by animating the reference along some directions by giving some points in this space, and then they will be the frames of the movie that will be generated with the VMD. Or you can group images that are close to each other and compute 3D reconstructions. So as I said, we have an extension of this method that works with subtomograms. In subtomogram analysis, you have additional problems like very much lower actually signal-to-noise ratio in the 3D data that you have normally in single particle analysis. So this is, for example, 3D reconstruction from without any noise. And here is the reconstruction with noise and the missing wedge that is due to the maximal tilt angle in the microscope that you see as missing data in the 3D Fourier space. So here you barely see the particle that you see here clearly. An additional problem is the crowded cell environment. For example, here you see nucleosomes in a very dense region of the cell. A classical approach to increase signal and correct for the missing wedge is subtomogram averaging that is based on rigid body alignment and classification and suitable to discrete conformational heterogeneity. So when you align the subtomograms, actually you kind of misalign the missing wedge in each of them. And then when you compute the average, you will attenuate the effect of this missing wedge because of this missing wedge that is then oriented differently, randomly in these subtomograms. So what we have done is that we extended the HEMNMA to 3D. So it takes as the input subtomograms. Here you see a particle very clearly in the subtomogram. This is just for the illustration. Normally you barely see the particle inside, and you need a 3D deformable model that can be either external, like atomic structure or EM map, or can be obtained through subtomogram averaging from these subtomograms. Then this map is used to deformed using normal modes and correlated with each of the subtomograms in order to get the conformation in each of the subtomograms. And then these conformational parameters that are again normal mode amplitudes are projected into lower dimensional space, in which the subtomograms are grouped and new subtomogram averages are computed, or molecular movies are generated by displacement of the formula reference along identified directions in this space. The flowchart of HEMNMA 3D is very similar to the one of HEMNMA. The most different step is this combined iterative elastic and rigid body alignment that here, as I said, is 3 to 3D before it was 3 to 2D, and also involves the missing wedge compensation. So actually what we are doing is that we are deforming the reference structure using normal modes and then performing rigid body alignment with the subtomogram with a missing wedge compensation, which means that we are maximizing the cross correlation between the deformed reference structure and the subtomogram only in the region where we have data in the Fourier space, not where we don't have data, meaning in the missing wedge region in the Fourier space. Here is an example of how this method works with nucleosome in situ data that we have done in collaboration with Amélie Le Forestier from LPS and Michael Edso from IGPMC in France. We know from previous works of on modeling of motions of nucleosomes. That nucleosome can adopt different motions like gapping, opening, and breathing. And our collaborators noticed in their experimental studies the variability of the nucleosome shapes, but they were unable to extensively study this variability because they didn't have tools for this, especially this for the continuous conformational variability. So we took their subtomogram average obtained from 650 subtomograms using classical subtomogram averaging. Here you see the model that has around 2 nanometer resolution, 4 views of the model of this density, and this density was then used to as the model to convert into pseudoatoms and then reanalyze these 650 subtomograms, and then we grouped the subtomograms in the most dense regions, and we obtained these average volumes. We have 4 of them, and here you see 4 different views of this complex. You see the number of subtomograms used in different averages, and we can notice that different actually degrees of gapping here in this view, or breathing here and here actually of the nucleosome. So to obtain this actually normal mode analysis of subtomogram, we use 6 modes here. So we use the first 5 lowest frequency highest collectivity modes, which means those for which the collectivity was above 0.5, and these 5 already included actually these 2 modes that I was mentioning, that are breathing and gapping, and we included one 6th mode that was a little bit higher mode that looked like interesting, but at the end with this data we could mostly see breathing and gapping in the final averages and even in the movies. We displaced the reference along 2 directions, D1 here and D2. Those are 10 frames of the movies in the 1 direction and in the 2 direction, and you can see here different degrees of gapping, and here breathing of the nucleosomes. And so this is how the graphical interface of HEMNMA3D looks like in Continuous Flex plugin of the latest version of Scipion 3. It is very similar to HEMNA, so I will not enter into all steps. The most differences you have in this part where we deal with the volumes. Before we had the images, so you have you can import volumes, series of volumes that you want to analyze. Then you can also synthesize volumes. As I said, you can synthesize, in this case, volumes with or without missing wedge, with or without noise and CTF, and yes, different parameters, rigid body parameters of the particle inside. And then you can also resize volumes and apply masks, which can be useful. Here with in situ, for example, data, sometimes we didn't in the nucleosome data case, we didn't apply any mask. And then you can also perform subtomogram averaging to get this, if you wish, the reference for the analysis of subtomograms. Otherwise, you can import it here either as an atomic structure or as a volume. And the other steps are similar, so I will quickly enter into these 2 steps that are in red subtomogram analysis, and in blue dimension reduction and analysis of the final results. So this is the graphical interface for subtomogram analysis using normal modes. that combines elastic and rigid body alignment. So as with images, you have this first tab is the same, except that you need to import volumes, not images. Then there is the second that is missing wedge compensation, in which you can either decide to compensate or not. You have to specify what was your tilt range. If you don't compensate, this means that we will take into account cross correlation over a whole sphere in Fourier space. And then you have the third tab here that is for combined elastic rigid body alignment parameters, where the parameters, this first parameter is the same as previously because we are using the same thrust region Paolo method for elastic alignment optimizer. And these two are related then to the rigid body alignment method, that is fast rotation matching in frequency space. And especially this parameter could be checked because this is the maximum shift that you want to search for in your data, actually, in pixels. And then the rest, the normal amplitudes, once they are computed, they can be displaced in this rose original space, that is the space of normal modes. We entered some, we actually have a few additional parameters here that we can change. For example, you can rescale this scale here for the colors. If this can be useful when you have several runs and then you want to compare different experiments on the same scale, and like this you can also compare, I mean visually, on the same scale different experiments according to same x axis limits and same y axis limits and z axis limits, so you can change these parameters limits. And then this part is the same as in the HEMNMA protocol. This is the dimension reduction, but I'm reminding you again here because once you got this display in the reduced dimension space, here is what you can get, because now we have a little difference with respect to what we had with HEMNMA. It is that in HEMNMA we were computing reconstructions, and here we are averaging the volumes by grouping volumes. You can compute an average volume, so you can see the slices, and with Chimera you can see the isosurface. So you get this tool by opening clustering tool as in HEMNMA, and then you have the second tool here that is trajectories, that allows you, as in HEMNMA, to compute animations. So we have worked very hard to get better testing of our protocols. So we have now new data for tests and new tests. So there are two tests basically for each of the protocols. So HEMNMA has two tests and HEMNMA-3D has two tests. The first test in both cases is testing entire protocol for atoms and for pseudoatoms. So you get drawn all, both trees, but the alignment module is not run. So we are reading the pre-computed parameters, pre-computed results, but in the second test we are really running the alignment using smaller number of images here and smaller number of volumes here. We are using 5 MPI threads to run this, to test that everything is fine. Here this is the most time consuming part of the protocol. So still one of these tests, so both, I mean in HEMNMA, takes around 3 minutes, even on a laptop, small laptop, and this also takes more or less 3 minutes to perform. So like this you can check that everything is fine, and this can be a good basis for you to start learning how to run it. So to conclude briefly, so I presented two methods, HEMNMA and HEMNMA-3D, that are available in continuous flex plugin of Scipion 3. HEMNMA is for single particle analysis in vitro of continuous conformational variability. It simultaneously obtains normal mode amplitudes, orientations, and shifts for each image. Images are analyzed independently from each other and in parallel. The method allows more extensive analysis of in vitro conformational variability of different architecture and sizes of complexes, which we showed in the past. And this new method is an extension of HEMNMA that allows continuous conformational variability in situ. Again, it is simultaneously getting normal mode amplitudes, orientation, and shifts for each subtomogram. Subtomograms are analyzed independently and in parallel. And I showed one example of more extensive analysis of in situ conformational variability of nucleosomes that has been recently accepted for publication. And with this, I would like to thank my team, especially to Mohammed Kharastani, who actually developed this HEMNMA-3D method and worked very hard to improve the graphical interface. Also, he developed this image and data and volume synthesis protocols in Python, and helped me to get these tests, automated tests of HEMNMA and HEMNMA-3D running now in this Scipion 3 latest version. And also I would like to thank two external collaborators, especially to Karasulab and together with Carlos Sanchez Orsano and all other members of their team for supporting our work since many years. And also our funding agencies, and I would like to thank to you for your attention. So this is the first part of the talk. So now I would like to show you maybe immediately this very short demo of the plugin, if you allow me. So I would first show you where this plugin is in the plugin manager of Scipion. So in order to use it, you need to install this Scipion EM continuous flex by clicking on it and then pressing this play button. It will install you some NMA libraries. And then you can perform what I showed you in this slide. You can type this command and this one afterwards on the command line, and then execute the test. So this test, I would like to enter into the test. So like this, I think you can see better what you have. So this will generate you 4 tests. One is test HEMNMA 1, then test HEMNMA 2, then test HEMNMA-3D 1, and test HEMNMA-3D 2. So if you enter into the first one, so this is what you are getting. So as I said, this is testing the whole protocol for atoms. So this part of the tree is for, together with particles, with images, this is for the protocol using an atomic structure as the input, and this one will be for pseudoatomic, actually for density map as the input. So if you start with the atomic structure, you have to import it. So this is our atomic structure, this is our toy model. You import it through this step here, and if you open our pre-computed now block here with the test that you will execute, you will get actually with which parameter we worked. Otherwise, you can import the volume. So here you would import through this field. So this is our EM map that we are imported. So you can see this is adenylate kinase, synthetic data, and the particles. So because we not only perform normal analysis, but we performed also image analysis. So these particles were imported through this field. So this is the set of particles that we are using in this test. So you don't have noise. Here there are 200 images of this size 128 square pixels. But you can, as I said, you can also synthesize some particles here if you wish. And these particles, because we want to synthesize particles with continuous conformational variability, you of course need to use some of the modes. For example, you want to use 2 modes, 7 and 8, to generate conformational variability with a linear relationship between the amplitudes that will be generated randomly, but you have different other distributions that you can choose. For example, you can get 3 clusters of conformations or a more regular kind of grid shape of the distribution, or totally random. So you need to specify what modes you want to use and the set of modes you want to use. So you need to recognize now which is which here to get the modes. And usually, I mean, I don't know, for people who are not used to Scipion, you need to see this is how I do. I mean, maybe there is some better way. I see the ID is 38 for here, for this side. So, and here is 472. So if I want to do this, so if I want to use the normal modes of the atomic structure, I need to select 38, protocol ID 38, because that was the normal set for atomic structure. Otherwise, I have to use another one. And what I didn't show you further, so you can apply noise and CTF, and you can determine here what specify what are the parameters of the CTF. And then you can also not only simulate rotations, but simulate also shifts, and this is the maximum shift that you can get. I mean, those are the default parameters. You can change them. So once you imported the input data, you can compute normal modes. Again, you have to press this and then fill in these fields. And in this test example, you will see immediately, I mean, what we used in the case of atomic structure. So we were computing 20 modes, and we used absolute mode. You remember I told you there are 2 modes, and for atomic structure we use absolute mode with the cutoff distance of 8. That was the default. All the other parameters are default parameters. While for pseudoatoms we used relative with this 95%. You need sometimes to open this a little bit to see it better, and even to press this advanced button to see really all parameters. So then when you have done the normal analysis, you can inspect the modes by playing the animations for each movie, for each mod, sorry. So mod 7 here, you get this animation. Then you can change to mod 8 and up to 20, because here we were animating only 20 mods. But usually you should actually compute more mods, more animation. 20 is usually not enough, so if you really want to be sure, it is better to compute 50 mods. at least. I mean, not at least, but generally this should be fine, 50. And then, as I said, you can get these maximum atom shifts for different atoms over all modes. So as you see, there is not one that is too far away going. So everything is fine with our cutoff parameter for interaction of atoms. And then you get the modes, the list of modes. As I said, we computed only 20, so we computed also these 6, but actually they are not checked in order to say to the user that they should not be used. And then you can order the modes according to the collectivity. So usually these first 6 modes are very highly collective, but sometimes you have some other modes that are a little bit higher frequency, but they can still be collective. So you should inspect this table. And so you get very similar movements if you look at the pseudoatomic structures that I didn't show you actually how we got it, but so these movies for the pseudoatoms are very similar. The modes are very similar. So basically you have the same visualization of these normal modes, but I skipped this step. Actually, this is the conversion of the map into pseudoatoms that you get at this step. There are some parameters that are here by default, and as I said, you principally don't need to change it, but except maybe perhaps sometimes this pseudoatom radius that is actually the standard deviation of the Gaussian functions, and this is the target approximation error with which you are approximating density with these Gaussian functions. So here, for example, you can see what we have used in this test. So you can also use the mask. In this particular case, there was no need to use mask because those were synthetic data very clean. But sometimes when you have experimental volumes, then you may want to mask the background, all this noise that is on the background. So there are different possibilities to make this mask, and you can inspect actually this conversion. So this is in gray the original density, and these blobs are Gaussian functions. And here these are the slides of the approximated volume. So again, when you decided which, you visualize the modes, you decide which modes to use, then you go to this step that is image analysis with normal modes. That you need to specify what set of normal modes you want to use. Again, if you want to use atomic normal modes, you use this one. You have to specify here some, otherwise all modes will be taken. Then you have to enter here the particles that you want to analyze, and again this field should stay empty. And here you have either valence splines that I always recommend if it's possible. If it's too time demanding, then you can reduce the size of the images by going to this step here. Otherwise you can use projection matching. And in this test, first test, number 1, as you will see, we were not executing this step, but we were reading the results that were computed previously, and we were using this to compute. And once you are done with this, you can visualize, because here in this test we use 3 modes, 7, 8, and 9. We can visualize in 3 dimensions our data. So this is our data in 3 dimensions. So each image is actually one conformation in this conformational space that is determined by the modes 7, 8, and 9. And you can also see only 2 dimensions if you wish. And the same, you would get exactly the same things for the pseudoatomic structure from I mean the same visualization modes. Actually, between atoms and pseudoatoms, you can have sometimes in the normal mode analysis change of the sign. This is normal. So because it's about oscillator types of movement, so actually both directions of the modes, because the modes are vectors, are valid. And then you can reduce the dimension of the conformational space by filling this field, so this dialog box. So you can choose one or the other depending on what was the conformational distribution you wanted to analyze. And here we provide actually 2 modes, like either to reduce the space to analyze the normal mode amplitudes, or the deformed models using these normal mode amplitudes. Actually, in this particular case, they should both get you the same results. So you can keep with normal mode amplitudes, and you can choose in this list various methods for dimension reduction, but the simplest is PCA, and this is the number of dimensions you want to see. So at the end you get 2 dimensions, or you can only see 1, because if you see 1, if you want 1, then you will get a histogram. If you see 2, you will get a 2D plot. So if you have 2 dimensions, you will get 2D plot. So again, like this, what I said, you can manually change these values, like from 0 to 0.0015. So you will see that this changed. Okay, it starts with 0. So this is if you want to compare different plots, and the same you can get for x, y, and z limits. So once you are done with this, you will see that here we got actually 2 tools, cluster and trajectory. So you can make clusters. Clusters means like manual interactive grouping for us. So you select, for example, like this, a number of images, and you add here the name of this group, and you press to create cluster. Press the create cluster button. This will generate, I will not do this because I just don't want to spoil this tree. You will get, for example, this kind of clusters. So you get whatever the images, you see that there were 55 images that enter into this group, and that the reconstruction from the images, from these images is this one, and you can also show it in Chimera. And additionally, you have a trajectories tool. So if you press here, you compute. You need to click on the first point and then on some end point, and then you will get a number of points in between. Then you can, if you give the name here, this trajectory will be saved, and then you can also revisualize it even out of Scipion. Or if you don't enter anything, then it will just generate animation. So in both cases you will get an animation like this one along this line. So here we are displacing this reference structure, this one, along this line in the reduced dimension space. So this is this first protocol, the first test, and the second test, as I said, in the second test we are going just up to this step that is image analysis, and we are really performing it. This is to test your MPIs. So in this case, as you will see, this field was empty, and we used a very small number of images, like 10 images, not 20, not 200, but 10. And the images were even reduced dimension. So you will see, for example, our 10 images that were reduced from 128 to 64 pixel. And this gives you this kind of distribution. I mean, that's normal. This is what you should obtain in this test. So that was to test the alignment. And in HEMNMA3D, you have the same idea. So you get a test with both parts drawn, like this is the subtomogram analysis using an atomic structure, and this would be the subtomogram analysis using a pseudoatomic structure as a reference. So in this case, we used exactly the same reference structures, atomic and EMAP as before, and subtomograms. As you will see, they are in this case really simulated subtomograms with missing wedge and with noise and CTF. So we have like 60 subtomograms that have been analyzed, but in these tests, HEMNMA3D 1, we are not analyzing those. We are just reading, as you will see, we are reading computed results previously. And you will see with which parameters we worked to compute this, and you get something like that. Again, you can, I think, show it in 3D because we used 3 modes here. And similarly, you can get to the 2D reduced space. Inside, you can also open clustering tool, do some grouping, and then when you say like give a name here and press create cluster, this will now compute you average subtomogram. Like here you will see our average subtomogram computed from 19 subtomograms. So this is our average. So if you look a little bit more carefully, you will see that we improved the contrast in this simple example, and also we attenuated the missing wedge. I mean, which you can see by this is how we look into this. We reslice this along y-axis. Then you can go to the middle slice. Then you go to image A, then you go to FFT, and you will see that this is more or less, I mean, field. While in the beginning, in the original subtomograms, if you displace one of those, like this one, for example, you do the same, like this. You go to the middle, go to image A, process, FFT, you'll see that you had the missing wedge. So again, you have also the possibility to do the trajectories if you wish. So again, the same, you go from here to here. So you will not see much difference with respect to what you saw with HEMNMA, because we were using the same references, but if you change, you will see the difference. And here I would like just to point you to this synthesis. Oh no, sorry, synthesis of volumes. So in this, you have this dialog box. You have the same principle as in the previous. So you have to select the normal modes you want to work with, and then specify the modes for example, two modes with linear relationship between the normal modes if you want to compute some conformational distribution based on these normal modes. And then also you can determine the specify the size of the volumes and everything. Missing wedge parameters, like you can also compute volumes without missing wedge or with missing wedge, and then you should here specify the parameters of the missing wedge, yes. Noise and CTF parameters, the reconstruction method if you want to change, and maximum shift of the particles in this subtomogram. And then there is Mohammed left this, but okay, this is not relevant to this protocol. You can compute the full tomogram if you wish. So this is yeah, and so the second is as I said, the same second test for HEMNMA3D is the same. It is just testing up to but really it is running the analysis of subtomograms. As you see, this field was empty. We were analyzing resized volumes that had, in this case, the resizing was done from 64 cube pixel to 32 cube pixels, and the subtomograms look like this, but we had only 3 subtomograms, so at the end you should get a picture like this one for the distribution. In this case, because the point of this test was just to test quickly the alignment. So this is all I wanted to show you in this talk. So now I'm open to questions. Already it is late, maybe.
Thank you, Slavica. There are a few questions in the chat, and if someone else has any other question, please feel free to ask. The first question comes from Carlos Oscar, and he asks, can the method benefit from previous 3D alignment?
You mean subtomogram alignment? Because this actually, yeah, we were testing this for HEMNA, so single particle analysis. Previous alignment, we didn't test this. My somehow feeling was that it would have been better not to align images, at least not to move them. Now, if you have some yes, file with pre-computed results, it is something that we should test, but we didn't test. I mean, it's not that easy to incorporate from outside this to our protocol now. But actually, I could show you this in the HEMNMA3D, because Mohammed was testing this. For example, here there is, I think, yeah, this is just for the subtomogram averaging, because this is there is a possibility in this HEMNMA3D to, as I said, import volume, synthesize volume, or maybe compute subtomogram averaging using our methods that is actually again based on this fast rotation matching. So going from scratch, or you can you can use some volume to align with respect to it. You know, to do this multiple reference iterations of subtomogram averaging and refinement, or you can import the alignment from Dynamo. Okay, he tested this. Apparently, this worked, but now I think I don't know. I think that the protocol is currently done really for the format of Dynamo. You cannot import any file, like, you know. But this is for getting the first reference. Okay, from the data, which is already, I think, quite important. So for the first reference, to get the subtomogram average from the data, you can eventually import the alignment parameters from something else, like the Dynamo. I don't know if you can import from anything. But in general, I don't think the protocol is easy to, at least it is not at this moment adapted to entering pre-computed parameters with some other alignment method, and we didn't test it.
Thank you, Slavi. There are more questions. That is there any advantage in calculating the normal modes in Cartesian coordinates or internal coordinates, or both are equivalent?
Yeah, I don't know if I can give a simple answer. I mean, I'm not really specialist for internal coordinates. I know that there are some people working in internal coordinates. I think that, I mean, now for normal modes especially, I'm not sure that this is better than Cartesian. But I know that, I mean, I understand that internal coordinates can be important in some other methods, like those molecular dynamics methods, for example, because you can maybe more easily compute some angles between atoms than in Cartesian coordinates. So this is about the implementation. But again, I'm not specialist, and I'm not sure that this is better or worse than using Cartesian coordinates for normal mode analysis, because normal mode analysis is a kind of simple method, and just by, I mean, at least the principle for the way we are using what I presented, which means this Cartesian method for the normal mode analysis, that is a kind of standard diagonalization of the Hessian matrix, full Hessian matrix. Now, I think that people who are working in internal coordinates, and when we speak about internal coordinates, we are speaking about atomic structures, okay? All these methods, in principle, in the beginning were developed mostly for when you don't have atomic structure. Now we are having more and more atomic structures every day. But if you don't want to use an atomic structure, then you don't speak about internal coordinates in principle, because internal coordinates are for atoms. This is how I understand. So now for atoms, we have this RTB method. I'm not sure that this would help, but I mean that it would be better. In any case, yeah, I cannot. I didn't try. I have an answer, but definitely, I would say you should better try these methods with structures that come from the data, which means not atomic structures, but reconstructions or subtomogram averages, or So which means then in this case you are using really Hessian diagonalization with the Cartesian method, so there are no internal coordinates.
Okay, thank you. Other question is, how sensitive is the method to the bond strength and the radius of interaction cutoff?
This strength, bond strength, it is not sensitive. This method, this particular method is not. But this cutoff radius, yes, of course, it is extremely sensitive. So that's why I spoke quite a lot about the cutoff radius, and this is why we have a kind of two methods. One is like to set externally the value if you are not, if you see that there is some problem, like you have few atoms that are moving kind of isolated from other atoms. When I say atoms, I mean also pseudoatoms. Sorry, I mean I'm interchanging actually both terms. So then if you see such kind of effects, then this means that there is something wrong with the cutoff. So you need to change. So you can externally maybe check what value for the cutoff would work better. Because, you know, if the cutoff is very small, then you get something that is very, very flexible. If the cutoff is big, too big, then you get something that is very rigid. So if it's something very rigid, then you get very few modes. For example, you want 20 modes, but the program will give you only 12. Or, you know, and then it will say, okay, there are some messages kind of to guide the user, but I agree this is not always easy, and that's why we have this automatic method to compute this cutoff, especially when you work with reference structures that come from data, which means reconstructions, or again what I said, subtomogram averages. Then this cutoff gets extremely important, I mean, to set properly. So I think that in the majority of cases, this automatic method that we have for setting the cutoff is working, which means when you have the data and you get an EM map from the data. And for atomic structures, the cutoffs that are set, like 8 angstrom, you can always change to, I don't know, 6, 7, 8, 9. But these values you more easily fix for atomic structures. For pseudoatomic structures, that is more difficult, and then you need to use this automatic tool.
Okay. One question regarding with the normal modes, the number of normal modes. What's the reaction of users when they have to choose the modes to explore?
I didn't understand your question. So you say, what is the reaction?
Of the users.
But
because you have different normal modes and you have to select.
How to select?
Yeah.
Yeah. Okay. So as I said, you remember we have for example, okay, here we have this table. Okay, so we have 20 modes here. They are 1, 2, 3 up to 20. So you have this collectivity of modes that you can order like this. You see now it is decreasing from 089 to 037. So you will say, because we know that the collectivity is always between 0 and 1. So you should set first some threshold like 0.5. But when you have many modes that are collective, like above 0.5, then you need to increase this threshold. You, for example, with virus capsids, all modes can be very collective, and all can be above 0.5. So you need to increase. So in these cases, you can use 0.7, for example. It's something that, yes, you need to check and to see those modes that are above the threshold, which means first you say, okay, in this case, let's say I can say above 0.5, this should be fine. So globally, I should have, I don't know, 1, 2, 3, I don't know, I cannot count now, a number of modes that I should in principle take. So once when I have, like from this table, I say, okay, there are 7 modes I have to check. So then I have to go one by one here and see first of all what are these modes, because sometimes for these structures that are symmetrical, for example, this one is simple asymmetrical, and it is much easier for normal modes to choose. But when the structure is symmetrical, then you can have many modes that are very similar. And even more difficult case is when you have pseudoatoms, then of course these modes are just approximations. So because they are approximation, they are not how to say perfect, which means that you can have several modes next to each other sometimes that are very similar. So it's a kind of spread of the same mode over several modes. So you would not take 3 of them if they are very similar. So you will take 1. So you need to check one by one with this VMD interface by changing here the numbers. So inspect all those that you found in this table that could be possibly relevant. And then you can also have some prior knowledge about the function of your complex and potential changes, which means that you, of course, are allowed to include, not to restrict to these motions, but to include inside. So it is always better to include more modes than less, because if everything goes well, then you get at the end only those modes that are really present in the data, that will get these amplitudes that will be higher, which means they will be contributing more to the transition. So it is always better to include a little bit more of modes, even if some modes you're not sure, but let's say for some you're sure because you suspect that this motion could be present, and then you have some that are very highly collective, and then it is better to include them. And yes, it is actually a combination of many different criteria that you have to use to select these modes. It is true that it is the most difficult step in this whole procedure. But globally, I mean, today we are having more computer power, and we are able to work with more modes than before. So, and yes, and what you can now use, because before I was not testing this so much, but now I tested recently, so you can really include more modes, but then you reduce the size of the image. Okay, and like this, your analysis will be still faster. But I always recommend to use these waivers and splines together with this reduction of the image size, and then you can include more modes. In my examples that I usually show 2-3 modes like this, because I think it's just enough for illustration. But you could take up to 10 modes, which is quite a large number.
I see. Thank you. Last questions comes from James, and he asked, can we quantify the similarity between atomic and pseudoatomic normal modes? And that's the first question. And the second one is there a way to find node correspondences and calculate correlation cosine overlaps?
Correspondences overlap between modes. You mean pseudoatomic and atomic?
You can see in the chat if you want the question.
Okay.
I think it's if there are a way to find...
node correspondence in calculation cosine overlaps. Node or mode? I think mode. I think mode. Okay. Yeah. For the first question, of course, that has been done many years ago. There are some papers. I don't even remember if that was 2004. from Florence Tama. Yes, there are some papers on this. So they have shown that atomic modes pseudoatomic modes approximate atomic modes when, of course, this cutoff radius is well set up. And yeah, I think that now I don't remember, but I saw some paper recently about this. How you can somehow do this correspondence between the atoms and pseudoatoms that we didn't test, but maybe we will do this. I'm not speaking about modes, but really about the correspondence between different atoms and pseudoatoms. But the correspondence between the modes, yes, you can overlap. All this has been done and published. So in my work, I mean, I was citing these older papers, so I assume that, again, under condition that you set properly your cutoff radius, pseudoatomic modes should approximate well the atomic modes. Now, of course, it depends probably also on the resolution of the map from which the pseudoatomic modes are computed. So there are more parameters, but in general, yes, you can make the correspondence, the overlap, yes.
Okay, thank you, Slavica. That's all.
That's all.
All questions were replied. So thank you for coming, and thank you for your talk.
Thank you really for the invitation. I forgot to thank the organizers, Jose, Luis, and Carlos Oscar, for this invitation. Yeah, it was a pleasure to speak about this, and especially to present this new protocol that is not that known yet, HEMNMA 3D for subtomogram analysis.